This week's batch of multimodal LLMs are completely insane. And in this video, I'm going to walk you through the basics of how you or someone at a large company with a lot of resources could train their own multimodal LLM. First, I'm just going to show you a brief video of the new features that came out this week in ChatGPT called GPT-4.0 or 4.0, just so you can see what's possible now. So let's just give this a quick play.
Hey, my friend and I are learning Spanish, and we're wondering if you could tell us the names of these objects in Spanish.
Hola, por supuesto.
Cool. What are these objects in Spanish?
The objects you're showing are una manzana and un plátano in Spanish. Nice fruit choice.
Cool.
That is super impressive. It blows me away. And the thing I'm going to focus on mostly in this video is how they do the multimodal part. Multimodal just means more than just text. So if a mode is text, when we're talking about multimodal, we're talking about incorporating things like audio and video into the same model as the text model, because that gives you just better performance and more stuff you can do, like you saw in that video. This is the paper we're going to go over to show how these multi-models get built nowadays. You can see here, over the last couple of years, since 2022, the number and diversity of multi-models has just absolutely exploded. From the early things like Flamingo a couple years ago, all to these latest batch of models that have just been taking off. A multimodal model has three parts. There's a modality encoder, and I'll explain what these are in a second. There's an LLM, and there's a connector. An LLM you're probably already familiar with, something like ChatGPT, but these other things might be less familiar to you, so I'm just going to explain what they are. First, the modality encoder. The modality encoder takes a different modality, like images, for example, and converts that image into a list of numbers, etc. This is our image, and this is our list of numbers. Another word that people use for a list of numbers like this is a vector or an embedding. So we have an image to an embedding. What's an example modality encoder that takes images to embeddings? Well, there's something called CLIP. I think it's helpful to look at an example so you can really get the idea. So this is CLIP, published by OpenAI in 2021. They were able to take an image like this one, and out of these many different labels that were available to them, pick the correct label. Or same for this image, it's a picture of a television studio, and they were able to figure it out of a group of 397 different other options. And this was the state of the art a couple of years ago. You take a picture, you had a list of labels available to you, and you were able to choose the correct label most of the time. CLIP was trained on a set of 400 million image to text pairs that they downloaded from the internet. In other words, they looked at pages like this Google page, for example, found a picture, found the associated text, and used that for their data set. And they found 400 million examples like that they were able to use. The prior art before that was something called ImageNet, where the makers of ImageNet got 25,000 people to annotate 14 million images over 22,000 object categories by hand. And the big innovation with this data set was they were able to download it from the internet. If you want your own data set that you can use to train one of these really, really large models, you can use something called Lion 400M, or I believe there's a new version called Lion 2 billion, which is a open source data set that you can train from. That comes from something called Common Crawl, which maintains a free open repository of web crawl data that can be used by anyone. I thought this was really interesting. I just learned about it. Over 250 billion pages spanning 17 years have been downloaded and are available. So you can check out Common Crawl if you want a big internet scale data set that you can draw from. But the main point of all that is that with CLIP, you have a way to turn an image into an embedding, into a string of numbers. So here we have our architecture we talked about before, our modality encoder, with the CLIP as our example, and we want to connect that to an LLM. Now LLMs, you may not know this, they take text, and they also convert that text into a list of numbers, which is also called an embedding. We want to connect our modality encoder, like CLIP, to an LLM, like ChatGPT. So you might think, oh, this is really easy. This is an embedding, and this is an embedding. I'll just take this embedding and jam it into the LLM. But that doesn't just work, unfortunately, because this kind of embedding is not the same shape and is not trained on the same data as this text data that went into the LLM training. So this embedding doesn't fit. It's kind of like the clip embeddings look like this, and the LLM embeddings look like this. And so they just don't match together. That's where you need something like Blip, which is a connector layer. This is the Blip paper. And what they do is they're able to take an image encoder like Clip and a large language model like ChatGPT, and they were trained something that they called a Q-former, which is basically the connector layer to connect between the outputs of the image encoder and the inputs to the large language model. There's a really nice paper about how they trained it. But the key outcome is that they're now able to connect their images to the LLM. And that gives you a very rudimentary and still very impressive multimodal large language model. And you can see here some results from the Blip paper about what they were able to do. So here, for example, you have an image, which is the Great Wall of China, and a prompt, tell me something about the history of this place. And it's able to tell something about the Great Wall of China. It's using Clip to recognize that it was the Great Wall of China, and it's using its LLM knowledge to spit out these other facts related to the Great Wall of China. So now we have our complete architecture. We have our modality encoder with an example being Clip. We have a connector with an example being Blip2. And we have an LLM with an example being ChatGPT. And these things can all get connected together. In order to build a world-class model nowadays, we have to train this. And training for a multimodal large language model nowadays involves 3 steps that each solve one of 3 different problems. The first problem is we have to connect images to text. Because after all, that's the new thing here. That's what the LLM didn't do, is we have to map between images and text. The second problem we have is we want more than just image descriptions. We're not just trying to do what Blip does, these short paragraphs. We really want to be able to converse with it like we can converse with ChatGPT. So in order to do that, we have to be able to instruct the model about what to do. So we do something called instruction tuning. And I'll tell you in a minute what that is. Finally, the last problem we have, which you may be familiar with, is that sometimes the models hallucinate, or they're inaccurate, or the results just don't feel good to a human. So we have to do some alignment tuning. We have to make sure that the model's results align with our expectations. So these are the 3 steps, and we're going to go through each one of them. The first step, to do image to text connections, they often call it pre-training. And here, you're using a data set similar to what they used to train Clip. Now, that's advanced quite a bit over the last couple of years since Clip came out. And now you have data sets with names like OpenClip, ClipVit, and various other things, which are the latest versions of the Clip modality encoder. And you can see what they're trained on. Lion 2B, so 2 billion element data set, OpenAI WIT, and other variations of Lion. A thing I should mention as well is the data sets for this sort of thing have been growing quite a bit over the last couple of years. People have been using models like ChatGPT-4 to build more detailed captions for images, and then retraining multimodal models using these new captions. So whereas the original caption data set was just data randomly downloaded from the internet, something like this data set called ShareGPT-4V has these really detailed captions you can use as you train out your model. Once you've done this image-to-text pre-training, essentially you have a model similar to this. Now, the next step we need to do is instruction tuning. I think one of the best ways to understand instruction tuning is to see an example of what a data set looks like. And one model that did that was released late in 2023, is called this Large Language and Vision Assistant, where they did instruction tuning on a multimodal model. So it's really helpful to see the kind of data that they're training on. You'll notice here we're not looking at just captions anymore. Here we have an image with some captions describing what's in it, along with some bounding boxes as inputs to the model. But in addition, we have some other training data. We have a conversation that you might have about this image. We have a detailed description, and we have some complex reasoning. So now all of this stuff is what's getting fed into the model that it can train on. You can see the results of having done this. So here's the blip. Here we have an image of a man ironing on the back of a taxi. And with blip 2, without the instruction tuning, the kind of answer you get is a man is sitting on the back of a yellow cab. With lava, with the instruction tuning, we see this much more correct and more accurate answer, which is that the unusual aspect of this image is a man ironing clothes on the back of a minivan. Here's another example from the data set. For example, when they ask Blip 2 about this picture of chicken nuggets that look like the world map, Blip 2 says, sometimes I just look at pictures of the Earth from space and marvel how beautiful it is, whereas Lava is able to recognize that this is a creative and humorous take on food with a focus on chicken nuggets. Finally, here they have some training details, and here you can see some examples of the kinds of prompts they're using and the way that they're training the data. You'll notice here they have many different ways of saying, hey, here is a prompt for this image. In this particular paper, they used an interesting trick where they used ChatGPT 4 to help them generate some of the data set that's going to go into their instruction tuning. And you can see their prompt here. I'll let you pause if you want to read through the prompt. And here again, you can see some examples of the kinds of things they're training on, captions and conversations and that sort of thing. So that's Lava, and that's instruction tuning, and the core insight that you should know about it is that it takes us from something like the result you get from Blip 2 into something that can really answer, like, why are these chicken nuggets weird? Really impressive. So now we've talked about two things. We've talked about image-to-text pre-training, and we've talked about instruction tuning. And now we're going to look at the last step, which is called alignment tuning. This is an example of alignment tuning. This is an adaptation of what we were just looking at, Lava, but now with this acronym, RLHF, which means Reinforcement Learning Human Feedback. So now you have a human in the loop giving feedback to the results from the model. This is the first time we've had that in this whole cycle. So I'm just going to give you some examples about how they do this. This is the instructions that they gave to a human. They say, we have developed an AI assistant adept at facilitating image-based conversations. However, it occasionally generates what we call hallucinations, which are inaccuracies unsupported by the image or real-world knowledge. So they ask the human, hey, here are two, we want you to evaluate these things for honesty and for helpfulness. We're going to give you two potential responses from our model, A or B, and some conversation context and an image, and we're going to ask which of these has fewer hallucinations and which response would be more helpful or less incorrect. Then they do some training, and I'll show you the kind of results you can get. So after going through this process of alignment tuning, here's how the results change. Here we have a photo of an airport in Texas, and Lava accurately says, so the question is, where is this photo taken? Lava says this photo is taken at an airport, which is not wrong. Lava, RLHF, after we've done our alignment tuning, gives this really accurate answer. The photo is taken in the baggage claim of an airport, specifically in the lobby of George Bush Intercontinental Airport in Houston, Texas. That's the kind of gain we get from doing the alignment tuning. Part of the power of this, part of the reason why it works, is humans are really good and really quick at recognizing hallucinations. So here's just an example one. Is the jam on the bread made of strawberry? You can immediately tell this bread has no jam on it. So in the original Lava, after the instruction tuning, after all that clip stuff, and Blip, Lava had thought, yes, the jam on the bread is made of strawberry. And a human can quickly give the feedback, no, there is no jam. We know that. And that's the sort of thing we're using to improve the model. So those are our three steps: image-text tuning, instruction tuning, and alignment tuning. Some interesting things I'll point out to you. For the image tuning and pre-training steps, we're using about 2 billion-ish data samples that were downloaded from the internet. As you get further down the pipeline, the data gets harder to collect, and so the volumes get smaller. So when we're looking at those instruction data sets, we're looking at hundreds of thousands of samples mostly, or maybe up to 1.5 million, as compared to 2 billion for the pre-training. So here, if we had 2 billion samples, here we're looking at about 1 million. When we start to look at alignment tuning, that paper I just showed you only had 10,000 samples in it. If I had to speculate, I would guess that over the next couple of years, the number of instruction tuning samples that are available is going to go up, and the number of alignment tuning samples that are available is going to go up, and both those things are probably going to help these models out quite a bit as they grow over the next couple of years. Now at the beginning here, I did talk a little bit about video, and I just wanted to very briefly go over how that works because we've been talking mostly about images so far. So just to give you a set, I know these are called multimodal models and we focused mostly on images. So I just wanted to give you a brief sense of how that might work for some other modalities. So here's something called ImageBind that came out from Meta in 2023. You can see here how they're looking at things like images and videos, depth tracking, text, but also other modalities like thermal imaging and IMU data. And they're combining all of that into a single model that's sort of similar to CLIP. It's a modality encoder, like we talked about earlier. So there are models coming out that are able to take many different modalities in addition to images and to embed them in one of these models, in one of the multimodal models. So just to do a quick review, we talked about 3 different parts of an architecture. We talked about a modality encoder, we talked about a connector, and we talked about an LLM. We also talked about 3 different things you do to train a model like this. There's a pre-training step, there's instruction tuning, and there's alignment tuning. Hopefully, going over this paper has given you a better idea of how a modern multimodal model is trained. If you're interested in more, I'll post a link to the paper down below. Thanks for watching!